Welcome back to our statistic learning session. Today we'll be talking about sample variance of chi-square distribution. Today we'll be talking about sample variance of a chi-square distribution, and here we have two important results we want to talk about in this slide. So let's begin. What are those two results? First, it's about sample variance, where it says that sample variance is the average of square deviation to the average and that's the first result we will talk about. It is squared is a deviation from the average of each of the points, and we square that and we take average of that, and that's the sample average sample variance. Second is the concurrence theorem, which states that given x1, given variable x, which is a identical and independent, and with a distribution of normal with the mu as a mean and mu and sigma square as a variance, then the sample variance of that distribution is independent of sample mean. This is really powerful statement. That's the first conclusion of Cochrane's theorem, and not only that, this is true for all n, and n may vary from 1 to infinity, but this is true for all n. This is really powerful conclusion. Secondly, what we want to say is that if you scale Sn properly, then the distribution of Sn is equal to chi-square distribution with freedom of n minus 1 degree. That's what we're going to say. This really powerful statement. Furthermore, we want to say is that we want to derive the unbiased estimate of sigma square, the variance of chi-square distribution. How do we do this? We start by writing down the expression of unbiased sample variance, which will be sigma, which will be Sn tilde. This is the unbiased one, unbiased sample variance, and for this, this is equal to 1 minus n minus 1, and it ranges from I1 to n and xi xn square. This is the unbiased sample variance. This is appropriate to divide sample variance by n minus 1 because Sn has only the degree of freedom of n minus 1. Sn, scaled properly, has a distribution of chi-square with degree of freedom n minus 1. Therefore, it is only appropriate to divide Sn by n minus 1 such that n minus 1 is negated. Now, what we will do is we will next step we will try to recreate Sn here by adding Sn by adding n at a numerator, and denominator will be n minus 1 times 1 minus n is equal to I is equal to 1 xi xn I square. From expression above, we know this, that n minus 1 equal to Sn. We know this. There's no problem in this. Next step, we want to find the expectation of Sn tilde. To do this, we will take expectation of Sn tilde, Sn, and same thing on right hand side, expectation n minus 1 Sn. Those are constant, n minus 1 is constant, therefore they will come outside of that bracket, and it will be expectation Sn, expectation of Sn. Now we will use the second point from the Cochrane's theorem that says that Sn has a chi-square distribution with n minus 1 degree of freedom, that is chi-square distribution with n minus 1 degree of freedom multiplied by sigma square and divided by n. Therefore, n minus 1 and expectation chi-square n minus 1 degree of freedom times sigma square n. Now, again, the sigma square and n will come out. Sigma square n minus 1 will come out. It will cancel each other, and we will have sigma square n minus 1, and expectation of chi-square n minus 1 degree of freedom will be n minus 1, which is equal to sigma square. This will give us the unbiased estimator of sigma square. Furthermore, what if you want to know the expectation of just Sn? Expectation of Sn. Not the expectation of unbiased sample variance, but expectation of just Sn. How do you do that? We can do that by taking Sn equal to sigma square n xn minus 1 equal to chi square n minus 1, and we'll take expectation of this. Expectation of Sn and expectation of chi square with a degree of freedom n minus 1. And we know that expectation of chi square n minus 1 equal to n minus 1. Therefore, the expectation of sample variance, not unbiased sample variance, the sample variance will be n minus 1 divided by n sigma square. In the end, let me quickly summarize what we learned today. We learned about sample variance, and for that we had the formula for sample variance, and we also for formula for unbiased sample variance, which is which had n minus 1 divisor than Sn. And also we talked about Cochrane's theorem, which stated two simple things. Sample variance is independent of sample mean. And also, if sample variance is scaled properly, then it has a distribution of chi square, which has an n minus 1 degree of freedom. Then we went ahead and did two calculations. One is a expectation of just sample variance, which gave us n minus 1 divided by n sigma square, and we did the expectation of unbiased sample variance, which gives us the value of sigma square. That's all for today. I'll see you next learning session. Thank you so much.